Welcome to your lesson 8.1 on model, inverse, and joint variation. So your objective today is that you're going to use inverse and joint variation models. If you'll recall, direct variation is something that we studied way back at the beginning of the year when we did linear functions, and that is y equals a times x. I have it there at the top of your notes. And a can't equal 0, and y equals a times x. And as x goes up, y goes up. As x goes down, y goes down. Now we're going to study two different kinds of variation, inverse and joint. First, we're going to talk about inverse variation. Two variables, x and y, show inverse variation if they are related as follows. Y equals a divided by x, and a is not equal to 0. The constant a is the constant of variation, and y is said to vary inversely with x. So y equals a over x, that's inverse variation. Y equals a times x, that's direct variation. Note the general equation for inverse variation, y equals a over x, can be rewritten as x times y equals a. Okay, so we're going to classify the following as direct variation, inverse variation, or neither. All right, so looking at our given equation, we have x times y equals 7. Let's solve for y. That gives us y equals 7 over x, which is inverse variation. For part B, we have y equals x plus 3. Well, neither kinds of variation allow us to add anything, so this is neither. Y over 4 equals x. Let's solve for y, so we'd multiply. So y equals 4 times x. That is direct variation. All right, so let's actually look at an inverse variation problem. The variables x and y vary inversely, so that tells us y equals a over x. And y equals 7 when x equals 4. That gives us a specific case so we can solve for a. Write an equation that relates x and y. We can do that. Then find y when x equals negative 2. Okay, after we have our equation, we can do that last part. So we write our general equation, y equals a divided by x. Then we plug in the specific pair that we were given, y equals 7 when x equals 4, so that we can solve for a. So 7 equals a over 4, multiply both sides by 4, and that gives us 28 equals a. So we know that in general, the equation is y equals 28 divided by x. So if we want to know y when x equals negative 2, we simply plug in negative 2 for x. So we get y equals 28 divided by negative 2, which gives us negative 14. Okay, the number of songs that can be stored on an MP3 player varies inversely with the average size of a song. A certain MP3 player can store 2,500 songs when the average size of the song is 4 megabytes. Write a model that gives the number n of songs that will fit on an MP3 player as a function of the average song size, s, and megabytes. So that means we're going to have n equals a over s because we want n as a function of s. Make a table showing the number of songs that will fit on the MP3 player if the average size of a song is 2 megabytes, 2.5 megabytes, 3 megabytes, and 5 megabytes as shown below. What happens to the number of songs as the average song size increases? All right, so our inverse variation model is going to be n equals a over s. Again, it's because we want number of songs as a function of size of song, so we're doing n equals a over s. We plug in the specific case we were given in the beginning of the problem. So we know we can have 2,500 songs when the average size is 4 megabytes, so we have 2,500 equals a over 4. So now to solve for a, we multiply by 4, and we get 10,000 equals a. So our model is n equals 10,000 divided by s. So now we can work on that table. On the table, we're given a bunch of average song sizes. So to get the number of songs, we just take 10,000 and divide by the song size. So 10,000 divided by 2 gives us 5,000, divided by 2.5 gives us 4,000, and so on. From the table, we can see that the number of songs that will fit on an MP3 player decreases as the average song size increases. So as we go from left to right, the average song size gets larger, and the number of songs gets smaller. And that's what it means to be inverse, for there to be an inverse variation. As one variable gets larger, the other one gets smaller. So we're going to check some data for an inverse variation. And we've got a table And it compares the area in square millimeters of a computer chip with the number C of chips that can be obtained from a silicon wafer. Write a model that gives C as a function of A, big A. So we're going to have C equals little a, our constant of variation, over big A, the area. We're going to predict the number of chips per wafer when the area of a chip is 81 square millimeters. All right, so we want to make sure we're not told anywhere that we have an inverse variation. We suspect that there's an inverse variation because if you look, as the area gets larger, the number of chips gets smaller. So what we're looking for is remember, if C equals little a over big A, then another way of writing that is C times big A equals little a. So what we're going to do is we're going to look at the product of each pair and see if it comes out to be approximately the same value. Now, because this is real world data, we can't expect it to be exactly the same value because that just doesn't happen very often in the real world. But we want them to be approximately the same value. So we're going to calculate the product of area times number of chips for each data pair in the table. And so we do that. So we start with 58 times 448 and we get 25,984 and we move through our pairs. 62 times 424 is 26,288. 66 times 392 is 25,872. 70 times 376 is equal to 26,320. They're not exactly equal to each other, but we don't expect that again because we're working with data. They do all round to be 26,000, so each product is approximately equal to 26,000. So the data show inverse variation, and we're going to model the relationship with A times C equals 26,000, or because we want the number of chips as a function of area, we're going to solve it for C. So C equals 26,000 divided by A. So we're going to make the prediction. The number of chips per wafer for a chip with an area of 81 square millimeters is C equals 26,000 divided by 81, which is approximately 321. So that is our prediction. We've used our model to predict the number of chips we'll be able to get from a single silicon wafer if the area of a chip is 81 square millimeters. Now, that's it for inverse variation. Let's talk about joint variation. Joint variation occurs when a quantity varies directly with the product of two or more other quantities. In an equation below, A is a non-zero constant, so again, A can't equal 0, and we have Z equals A times XY. So we say Z varies jointly with X and Y. All right, the variable Z varies jointly with X and Y. So that tells us that we can use the model Z equals A times X times Y. Also, Z equals negative 75 when X equals 3 and Y equals negative 5. They've given us all three values so that we can figure out the value of A. And this will let us do what the next sentence asks us to do. Write an equation that relates X, Y, and Z. If we can figure out the constant of variation, we can do that. Then find Z when X equals 2 and Y equals 6. So once we have our equation, we can do what the last sentence asks us to do. All right, so our solution, we're going to write a general joint variation equation, Z equals A times XY. And then we're going to use the given values of Z, X, and Y to find the constant of variation A. So we're going to substitute negative 75 for Z, 3 for X, and negative 5 for Y. And so we get negative 75 equals A times 3 times negative 5. We simplify, we get negative 75 equals negative 15 times A. Divide both sides by negative 15, and we get 5 equals A. Okay, so Z equals 5 times X times Y. All right, now we're going to calculate Z when X equals 2 and Y equals 6 using substitution because we've got our model. Now we can figure out a specific value for Z given particular values for X and Y. So Z equals 5 times X times Y, so that's 5 times 2 times 6, and that gives us 60. Okay, that's it. That's all there is to it. So do the problems to try on your own. Come to class ready to go over them and ready to get started on your rounds. Have a good day. I will see you in class.